analyte. And the concentration of your analyte in the stationary phase versus the concentration of the analyte in the mobile phase. Right? So naturally, things that partition more strongly to the functional group in the stationary phase will have a higher partitioning coefficient, by this definition. And things that partition very poorly or very weakly onto the stationary phase will have a very low partitioning coefficient. If an analyte that we add does not partition at all into the stationary phase, then it'll essentially wash out the mobile phase. Things that don't bind at all to whatever the stationary phase is. So we have a basic concept that needs to be very clear, that when we're talking about chromatographic separations between two phases, what we're trying to describe and what we're trying to understand is the extent that our analyte partitions to one phase more strongly than another, right? And that our ability to separate mixtures of analytes, of course, depends upon the fact that those different analytes all possess different partitioning coefficients. If they possess the same partition coefficient, two different analytes, they will co-elute together, and we won't see them as different. We'll see them as one thing. And in many chromatographic separations, and you'll discover this, you get peaks. This is some response from the instrument, whatever the detector is. And for chromatographic separations in chromatograms, the x-axis is almost always, for most applications, is time. And the y-axis is the instrument response, depending on what kind of detector and analytes are being analyzed. And there's always a time 0, and there's some time x out here, and the time 0 reflects when samples are loaded onto the column, injected onto the column. And typically, in this kind of a chromatogram, which is so classic, when things are loaded onto the column here at time 0, and then they start detecting, usually after some amount of time, there's a small peak that loops out that reflects the composition of the aqueous phase that your sample was in, your sample, not your analytes. So this is essentially just what they call the volume and the time it takes to go from the top of the column to hitting the detector. So in most cases, you see some kind of a little peak like that because the mobile phase is chemically a different composition than the composition of the matrix that your sample is dissolved in. So in your case, you'll say, my sample is natural water sample, groundwater sample. And the mobile phase will be an acetate buffer, okay, made up in water, and which has a slightly different composition than just the groundwater sample itself, which is not made in acetate buffer, right? And so when you load your sample on, and that water that essentially is your groundwater sample, that water will flow through with the mobile phase, and when it comes out of the detector, in your case you're measuring conductance because you're measuring ions. The groundwater sample, which is just fresh water generally, has a different conductance than the mobile phase itself, and you measure that, and your detector has this small little peak of a response, right? So this time here then tells you something about how long it takes for something to come out. Okay. And then nothing happens, and then maybe finally your analyte comes out. Hopefully not shaped like that. Okay. And you'll look at this, and you'll say, okay, this is the time it takes for just the mobile phase to transit through the column, right? And this is the time it takes for if I only had one compound in my sample, for that to actually lead out for me to detect that. And so there's several things we can get from this. One is that we know this is time 0. I'm going to make this right here, this axis. That's time 0 when I injected something right there. Okay, at time 0. We know that then that there's a total time it takes for my analyte to elute. Okay. And we typically refer to that time from the time I inject when my analyte comes out as the retention time. CR reflects the retention time of your analyte. And there's also a time here that's referred to where essentially just the time it takes for the mobile phase to push that sample matrix, not counting not your analytes, but the things that don't partition to the stationary phase through. And that's referred to as the T sub m, or the mobile phase elution time. And then the difference between these two, which is just this, is essentially the time it takes for your analyte to elute, or the sample elution time. Okay. So, in many cases, if you have multiple compounds, then you would get, some other compound coming out here, and it would have a different retention time, right? And in the case of your samples, it's quite likely that the unknown samples you'll be separating, there'll be 3, 4, 5 different anions in there that will chromatograph at different times over the course of about 20 minutes. So, one of the challenges of chromatography, and I'll talk about this in terms of relates to how you can do your lab, is that typically these separations take a fair amount of time. And we know that, and we'll talk about this in great detail next time, we know that if I had a column like this versus a column like this, assuming the outer diameters are the same, the longer the column is, the more stationary material is packed inside. The more stationary material that's packed inside, the greater the number of surfaces or interacting chemical groups there are on which your analyte can partition onto. So there's generally a substantial difference in how well you can resolve mixtures of compounds with smaller, shorter columns compared to longer columns. Usually you get much greater separation power or efficiency with these longer columns than you do with shorter columns. And the difference then is that the amount of time it takes to actually elute things successfully on these longer columns generally is substantially greater. So in many chromatographic methods that are using sort of just very basic separations, the gross qualitative separations, you might be able to perform an elution over the course of 5 minutes. In your class, where you have a column that I think is 25 centimeters long, which is for high pressure kind of chromatographic methods, is pretty typical. It'll take you about 20 minutes to separate one sample. And that's going to create some challenges for us, for you, in actually conducting the lab in sort of a timely way. And I'll talk about how we're going to approach that. Okay, so fundamentally, we look at these chromatograms, and we can look at something like the columns in this chromatogram, and we have these very important parameters that we're going to utilize in order for us to be able to characterize our samples. Now, let me erase this, but I assume you're going to remember this. When you actually start generating chromatograms of your own, you're going to get a peak here, maybe a peak here, and each of these peaks will have their own specific retention time. And in fact, one of the ways that you're going to identify peaks is when you load a standard that has a mixture of many different anions, and you create a chromatogram with that standard, and you're going to look at the chromatogram that the manufacturer of the standard gives you, and they're going to say that on this column, that chloride should come here, and this should be fluoride, and this should be bromide, and this should be nitrate, and this should be, and you're going to get some elution sequence of the anions in that standard that hopefully will look something like the chromatogram that the manufacturer provides, what the standard provides to you for that particular column. And you're going to use that chromatogram to different retention times of those known compounds in the standard to identify the unknown peaks in your sample. Because one mixture of a sample will contain 5 or 6 or many different anions. Well, will generate many different peaks. And what you're going to find is that in your chromatogram, there may be 10 peaks there, and the standard has 5. And you can say, okay, I can identify 5 of my peaks, but I have no idea what these other 5 are. And then maybe you'll have an opportunity to try to explore identifying what they are, so you can actually characterize them. And how you're going to characterize them is going to be based on their relative retention times. Because that tells you a lot about how those different compounds are partitioning to the stationary phase.
What if the peaks are overlapping?
So, it's really common that you'll elute something and you won't get a peak that looks like this. Maybe you'll get a peak that looks like that. And you'll be like, what is that? And or more common, you'll come out and go like that. And you'll be like, what are those things? They're not eluting they're not eluting separately. And now I'm wondering, do I have multiple peaks under this big mountain, this hump? Or is that just a characteristic of how this particular analyte is eluting with this column because of something, you know? And oftentimes it's both, it's one or the other, right? Many times in chromatography you have coelution of analytes in a peak and you don't know it, right? Unless you look very closely at the shoulders of those peaks and try to get a sense of what that looks like. Because ideally a peak should look somewhat normal, like this, or have a nice decreasing function as a tail coming off, depending on how much of the compound's on there. And when you see irregularities like that, that's a clue that there may be something else there. And then you're faced with then you're faced like, what do I do? How do I separate these? And that becomes the science of chromatography. People will spend, and I'll talk about this next time, people and companies spend an enormous amount of money in research and development in trying to design different kinds of solids, different kinds of stationary phases, in order to elute different kinds of analytes separately and separate them, right? It becomes very challenging. And you not only have, of course, the composition of the stationary phase in facilitating this, but you have the composition of the mobile phase that does this, that affects this.
Why can't you just use the longer chromatographic column?
Because if two compounds are very similar chemically, then a longer column, first of all, the longer the column, the more the dilution of the sample occurs. And as the sample gets dilute, the peak height that you're going to attain shrinks, right? Because it's spread, instead of looking like that, it starts to look at the end of the column like that, right? So that's one problem. So a longer column doesn't necessarily solve that. Okay? What typically does solve is changing the kind of chemistry, modifying the chemistry that's occurring.
If you got overlapping peaks like that and you diluted your sample and made it again, would that, I mean, that would make the peaks smaller, but would that theoretically separate them even more? Or would it just...
If you, now since we're dealing with partitioning, right, and there are a fixed number of partitioning sites in the stationary phase, if you have too much analyte that you load on and you overload your column, of course that will dramatically impact the resolution of the separated peaks, right? So typically we avoid that from the start. Right? And if you have something like this, and which is quite common, you'll see this in many groundwater samples, especially in the Monterey Bay, the ones close to the ocean, for the groundwaters, the fresh water from the aquifers, there's, because of aquifer over pumping, there's saltwater intrusion. And you've probably heard of that problem, right? Now, if your job is to you're working for a consulting company and you want to characterize levels of bromide or nitrate in the groundwater as evidence of seepage from decades of fertilizer use, which people are concerned about, and in that sample there's some saltwater intrusion, when you go to measure, what you're going to find is you're going to find a chloride peak that goes off the scale and goes up to the ceiling, because there's a lot of chloride in salt water, and it's going to mask the things you're looking for. And it becomes very, very challenging. And you're going to see that when you run your samples, and some of them I think, you're going to find it's like, oh my gosh, one of my analytes is so high that if I dilute it down so that I can measure it with my standards, all the other analytes are like little bumps, and I can't see them. And so you may have to say, okay, I've got to run one sample that's not diluted, and I can't measure this, can't quantify because it's off the charts. And I have to run another sample, and then I quantify these. And I have to run a separate sample where I do dilute it, and I can't measure these, but I'll measure that. That's not uncommon, right? Okay, so we just talked about all this, right? So, and we just went over all this, and we don't need to belabor that. So, there's a relationship, as I mentioned here, in terms of the resolving power based on how long the columns are. And this is meant to just sort of reflect that you have these two analytes and a sample mixture, that the longer they migrate through the column, typically, the greater you're able to separate those compounds on a chromatographic column. And that's one reason why people don't use short little columns like this. They use longer ones like this to facilitate that separation. And this is an example of an incompletely separated mixture of these two things where there's substantial overlap versus fully separated. And the way that you typically quantify these will be the same way we've done so far, and that is you'll have an external standard curve of known concentrations of different anions that you analyze at different concentrations. You generate a standard curve for each anion. You'll do that. And then you'll quantify each peak, not by the peak height, which would be sufficient to quantify these, but by the peak area. And you couldn't do this, right? Because you won't see this, all you see is that. Right? And so some software programs allow you to model these peaks when there's overlapping peaks and infer what this peak shape looked like, so you can integrate all of this, separate from integrating all of that. But that requires the assumption that the algorithm makes an assumption that the peak shape follows this kind of trajectory. A lot of times they do, but sometimes they do not, especially on this end. Okay. So you're far better off actually resolving and separating peaks, so that then you can say, where's my baseline? And I'm going to integrate this peak area from here to there. And I get that peak area, and I'm going to do this peak area from there to there. And you're going to be comparing peak areas, not peak heights. Right? Okay. So this is an example, a stylized example of what I was drawing earlier, that you have a column that's packed with a stationary phase. It could be beads. Typically it's some kind of a small bead that's made out of something. In this example, it's a latex bead. And on that bead, it's got these functionalized groups, and at the end of it has some functional group that is imparting chemical character on that bead. And so there's huge surface area on each bead, and then there's typically tens of thousands of these little beads that are packed in a column at the pressure, so that as the fluid flows through, the mobile phase flows through, then your dissolved analytes are interacting, in your case, electrostatically with these quaternary ammonium groups, which is what you will be doing, right? Now, when you pack columns with these beads somewhat tightly to maximize the surface area of these functional groups that may interact with your analyte that's passing through the mobile phase, that creates a lot of resistance to flow to the mobile phase. And that's why most chromatographic systems, like the one you'll use, and like all high performance or high pressure, people use both terms, liquid chromatography, is that they build up a lot of pressure in the fluid. It takes a lot of pressure to push the mobile phase through, because there's a lot of resistance because those beads are packed so tightly. And so the pressure in your system, I'm guessing now, I'm trying to remember what it is, it'll probably be about 1,200 psi. So at 1,200 pounds per square inch, which is pretty good for, but the tubing is this peak tubing that's about, maybe 0.1 millimeter in inner diameter. So really skinny tubing, the inner diameter is really skinny, that's attached with these high pressure fittings onto a column that generates these special pumps that are able to generate high pressures without leaking and without generating any pump noise. It would generate a sort of a oscillating background signal. Okay. So let me take a few minutes to kind of step through some of these things that we kind of want to be aware of. I want to sort of redraw the stylized chromatogram. We always have time there. We have some response here. That's time 0. That's time whatever. We inject our sample. A mobile phase, transit time becomes evident. And then at some point, our analyte becomes evident. And then we have what we refer to as our retention time of our mobile phase. And then we have the retention time of our sample. And then we can also calculate the actual difference between the mobile phase transit time and the total retention of our sample is saying how long is our sample partitioned onto the stationary phase, which is what this T sub S3 does. So we know that underlying all this is we have a very simple partitioning relationship where we're looking at the concentration of our analyte that partitions in the stationary phase versus the concentration of analyte that partitions in the mobile phase, right? And so we're able to relate this retention time of our sample actually to the partitioning coefficient of our analyte onto the stationary phase, which is this. Okay. And so this is kind of how we can do that. We can look at a number of different terms, and so we can look at this V term as relating to the velocity of our analyte through the column. Okay. And we can use mu to reflect the velocity of our mobile phase. Okay. And now, let's take a step back and make sure we're clear on something. So when we generate a chromatogram, all chromatograms, for the most part, that we'll be talking about, have time on the x-axis. Okay? And so when we think of velocity, what we're talking about here is some length over time. Okay? And we know the length because we know how long our column is. So in our case, if we're using a 25 centimeter column, and we know the time for the mobile phase or for our sample to migrate through that column, we can easily determine the velocity of our mobile phase or the velocity of our analyte in terms of length, because we know how long the column is, because we know how long it takes it to go through the column, and we know how long the column is, that we can easily calculate the centimeters per second, for example, of both our analyte or of our mobile phase, right? And so some of these terms are looking at actual units of length and distance in terms of velocity as opposed to time, but we can easily determine one or the other because the column length is always fixed. It varies from one system to another, but it's used for all the separation of that system. So now we can say, well, all right, the velocity of my analyte through the column, how fast it goes through the column. Now, and this is really, we're looking at time, how long it takes to go through, and what distance it traveled in our column length. So the velocity of our analyte goes through the column is going to be a function of how fast the mobile phase is going, whether we're pumping at 1 milliminute, 5 mils a minute, or whatever. Right? And it's going to then look at the partitioning and a function of the partitioning of our analyte in the mobile phase versus the total amount of analyte in the mixture. Okay. And so this is just looking now at the velocity of our analyte going through the column, right? And so you're envisioning that the analyte is loaded here in the column and it's transiting through it at some velocity, and it comes out and gets detected here. Okay. And so the velocity of going from here to here is simply going to be a function of how fast the mobile phase is going through, how fast the river is flowing, right? How much total analyte is in the mobile phase compared to how much total analyte is there completely, right? And so this is a total amount of sample I load, analyte I load, and this is the total I load minus how much is stuck on the stationary phase. Simple as that, right? So that makes sense, I think, at least to me. So then we can, knowing what we know, we can then rearrange this and convert this to look at the velocity of the analyte that's going through our column, knowing the velocity of the mobile phase is going through our column. And then we can break this down and say, well, the moles of the analyte in the mobile phase is going to be essentially the concentration in the mobile phase times the volume of the mobile phase, right? That makes sense. And the total number of analyte moles in the column itself is just going to be the concentration of the analyte in the mobile phase and the volume of that, plus the concentration of the analyte in the stationary phase and the volume of that, right? So this is everything in the column, and this is just that proportion that's in the mobile phase. That makes sense, right? So knowing that, then I can say, well, then I can simplify this and say, if I look at this gets reduced to this when I combine these terms, that I can then know just essentially the ratio of the concentration in the stationary phase times the volume to the concentration of the mobile phase times the volume. Right? And then if I know that the partitioning coefficient is essentially the concentration in the stationary or the mobile phase, I can then simplify this, and I can simplify it down to this simple term here where I say the velocity of my analyte in the column, right, is going to be a function of the velocity of the mobile phase, how fast things are flowing, and the partitioning coefficient times the volume of the stationary phase and the volume of the mobile phase. Right? So all this is just sort of going around saying, how do I relate something that I'm going to actually measure, physically measure? I measure these times. It's easy to do that. Okay? To using that information to understand this, which is much more difficult to measure. And this becomes important because this is what determines my ability to separate one analyte from another. How extensively partitions in the stationary phase compared to the mobile phase. Okay? And so this kind of helps us understand that process just from a theoretical perspective. Now I can go a step further and I can say, what we really care about is retention. When we think about chromatography and we think about our ability to separate compounds from one another chromatographically, what allows us to do that is the assumption that these compounds that we're trying to separate are retained on the column to different degrees. And when we say they're retained on the column to different degrees, all that means is they partition, they have higher, modes that are retained longer on the column, partition more strongly in the stationary phase compared to the mobile phase, right? That's all we're talking about. And so retention is a key term that describes how these compounds are sticking on to the stationary phase and how that may differ from one compound to the other. And so we could use that understanding then to derive a factor called a retention factor, which is a factor that's going to be specific for every compound. And we could use that then to understand when we're designing an experiment, people do this to understand the effectiveness that we think we might have in separating different compounds from a mixture. Okay. Now, where this really happens and where people really use this is they don't sort of sit down a priori ahead of time and say, here's some unknown sample, it's got stuff in it, and now I'm going to go through and try to estimate some retention factors for the different things that I'm trying to measure in that sample. They don't necessarily take that tack. What they do is they say, all right, I'm going to inject my sample on my column, and what I first get is a chromatogram that looks like this. When the first thing you recognize is I'm not effectively separating these compounds that I want to separate and quantify. So I can go ahead now, based on this, I can actually calculate under these conditions what the retention factor is for each of these analytes. And then I'm going to go and start modifying things, maybe the composition of my mobile phase, maybe the speed of the mobile phase, maybe the type of column I'm using. I'm going to make some experimental decisions to modify the properties of something that I have in my experiment in order to change those retention factors so that they are more different. Because the retention factors that are more different, of course, would reflect that I am able to separate things more effectively. And so then when I write up my method, I'm going to be able to actually publish or report what my retention factors were under the conditions that I made up and optimized for these different compounds. And then people can use that information in which to optimize maybe some separation schemes that they're involved with. So the retention factor is something that's derived from knowing about the partition coefficient. And we know that the partition coefficient is something that reflects units of concentration. Okay? And the retention factors essentially just has units in moles. We're looking at essentially the number of moles that's partitioned in the stationary phase, not a concentration, the number of moles, versus the number of moles that's partitioned in the mobile phase, right? And so the definition is very simple, just like that. And so we can say for compound A, that we can calculate a retention factor for A by knowing the partitioning coefficient, right, which we don't quite know yet, right? It's theoretical. And then look at the volume of the stationary phase and the volume of the mobile phase. And when we go through that math, that's essentially just telling us the number of moles of each of the compound in each of those two phases, right? So if we start from where we were on the slide before, where we know that the velocity of our analyte in the mobile phase is going to be a function of these parameters, the partitioning, the volume of the stationary mobile phase, and so forth. And we can simplify this and look then at the relationship with the velocity of our analyte in the mobile phase is going to be a function of all this, where now we can substitute for Ka for all this, the retention factor. Right? So this gets simplified to this, knowing that this term here is this term right there, okay, for the retention factor. And then we can simplify it a little further. That's where we left off now. These are still somewhat theoretical things that are difficult to actually measure. But now we're saying, I want to understand still the extent of partitioning of my analyte in the stationary or mobile phase. I can now prove that I can mathematically derive that formula at the top, where I'm looking at the velocity of my analyte in the mobile phase. It's going to be a function of the velocity of the mobile phase and the retention factor of that compound, right, which are the number of moles in the stationary mobile phase. Then I can say, well, the velocity of my analyte in the mobile phase is simply the length of my column, 25 centimeters in your case, and the retention time that I can measure from my chromatogram. And that the velocity of my mobile phase is essentially be the length of my column, 25 centimeters, times the mobile phase retention time, Tm, that I measure. Right? If I know that, then I can substitute those terms and rearrange, and then I can calculate my retention factor is essentially a function of the TR minus the TM, which gives you TS in this example, divided by the mobile phase retention time. And that is something that I can measure. Right? So I can take all the theoretical rearrangements of those equations I just showed, and I can actually derive a retention factor for each of these compounds from the information I can easily get out of my chromatogram. And that's the point. That's what you'll be doing. And so as an analyst, you would be essentially doing that and using the calculated retention time, retention factors, for your compounds under normal conditions to optimize your separation methodology so that you can maximize those, right? The more different those are between compounds in a mixture, the more effective you are at separating them. Okay. I'm going to come back to this next time. Okay, so we have a few minutes left. Has anybody downloaded Lab 2 yet? No, I didn't think so. All right. You got a lot on your plates. This is the first page of Lab 2. And this tells you what you're going to be doing. I already sort of described this, what your objectives are. Lab 2 is a little bit more different, a little different than Lab 1, aside from the chromatography and all the method of the instrumentation. And the main difference is that because it takes so